SpaceX's Starship is currently humanity's best hope for landing on Mars this century. There is no denying that, in the future, Starship will have enough power to carry both crew and a huge amount of cargo to Mars. However, a big question remains: how to return from the surface of this red planet. This is the most complex technical challenge in the journey, the moment that determines success or failure. Space Now channel will join you to learn more deeply about the technologies, strategies, and solutions that SpaceX is developing to overcome this barrier, opening the door for the first flights back from Mars. Landing on Mars is not simply a flying down operation like landing on Earth. This is a complex problem, requiring high technology and precise calculation ability. Before understanding how Starship lands on Mars, we need to understand the journey from Earth to this planet. The most important thing about space travel is to always remember that everything in space is moving. When it comes to a solar system, the planets are always moving around the Sun in certain orbits. We, along with all the planets in the solar system, are pulled towards the Sun by gravity, and the only thing that prevents us from falling into the Sun is the Earth's orbital speed, about 30 kilometers per second. It is this speed that helps the Earth maintain its orbit, moving steadily around the Sun in 365 days. Mars, because it is farther from the Sun than the Earth, is not pulled as strongly as we are, so the planet can move at a slower speed, about 24 kilometers per second. So how can we leave Earth and fly to Mars? The answer lies in changing the speed of the spacecraft. When we launch from Earth, the spacecraft becomes an object in orbit around the Sun. If the spacecraft slows down, it will fall into the orbit of a planet closer to the Sun, such as Venus. Conversely, if it speeds up, it will move outwards into the solar system, closer to Mars. This process is called relative velocity change, or delta V, an important term in space travel. Simply put, if the Earth is moving at 30 kilometers per second and the spacecraft accelerates to 31 kilometers per second, the change in velocity is 1 kilometer per second. This means that when we change the spacecraft's speed, we change its trajectory, guiding the spacecraft toward the target planet. Do you think that when Starship changes velocity, how will this affect its ability to land accurately on Mars? Leave your comments in the comment section below this video. This also highlights the importance of testing and simulation before actual flights. SpaceX's Starship is not just a space vehicle, but also an important breakthrough in applying new technology to master space and open the door to conquering planets beyond Earth. When we start our journey from Earth, it is clear that we cannot easily cross the Earth's surface because gravity and atmospheric resistance are holding us back. It is these natural factors that will determine the amount of delta V, change in velocity, needed for the spacecraft to move. That is why leaving the Earth's surface and entering space is such a huge challenge. To achieve a low Earth orbit, delta V is needed at about 9.4 kilometers per second. This is a huge acceleration, and so Starship needs a super powerful engine like the Super Heavy booster right from the start. Another reason why Starship would need to stop to refuel in Earth orbit is because we would need a lot of delta V to continue our journey to Mars. To change velocity, we need engines, and engines need fuel. Refueling in Earth orbit has the advantage of being able to reset our starting point. After refueling, we would only need to add 9.5 kilometers per second of delta V to reach the velocity needed to enter the Martian surface, a number close to the velocity needed to escape Earth's atmosphere. However, this does not mean that the rest of the journey would be simple, as the approach would be very different. While leaving Earth requires us to accelerate vigorously, landing on Mars requires us to decelerate, which is equally complex. A fully fueled Starship in Earth orbit is expected to have enough thrust to reach around 6 to 7 kilometers per second or delta V. This is obviously not enough compared to the 9.5 kilometers per second needed to reach Mars, but this is not a big problem, because natural forces, including gravity and atmospheric drag, will give the Starship more thrust when approaching and landing on Mars. So how does this work? We will be in Earth orbit, and even though we are a few hundred kilometers above the surface, we are still caught in the gravity of the Earth. At this point, only velocity will keep the Starship from falling back to Earth. If the spacecraft slows down, it will start to fall, but if it speeds up, it will continue to fly into space. However, close to Earth, we need a huge amount of delta V to counteract the gravity. To reach geostationary orbit, the spacecraft will need to accelerate by 2.44 kilometers per second. And to reach the altitude of the Moon, we need another 0.68 kilometers per second. Once outside Earth's orbit, we are effectively at the edge of the planet's gravitational influence. Although gravity is infinite, its pull diminishes with distance. Now, to escape Earth's influence completely, we only need another 0.9 kilometers per second to leave the planet's orbit. Once we reach deep space, past the Moon, the transition to the velocity needed to travel to Mars will only require 0.39 meters per second of delta V. This part of the journey will consume about 3.6 kilometers per second of delta V, which is a large part of the Starship's energy, but this is only the first part of the long journey. Having expended a huge amount of fuel escaping Earth, we now face a major problem on our journey to Mars. We no longer have enough fuel to land successfully using the engines alone. The reason is that all the speed we have gained escaping Earth's atmosphere and gravity has us moving around the Sun at a much faster speed than Earth, which moves at about 30 kilometers per second. Mars, meanwhile, is only moving at about 24 kilometers per second, meaning we are overshooting our target and risk straying into the asteroid belt unless we start slowing down. After a few months of drifting in space, we need to make our first deceleration. This requires rotating the Starship and restarting the Raptor engine, slowing it down by another 0.67 kilometers per second, enough to get the spacecraft into Mars's gravitational orbit. Next, if we slow down another 0.34 kilometers per second, we will reach the orbit of the outer moon of Mars, Deimos. A little further, another 0.4 kilometers per second, we will approach Phobos, the largest moon of Mars. However, this is where things get extremely complicated. Such a deceleration has consumed more than 5 kilometers per second of delta V, almost depleting the spacecraft's fuel supply. At this point, there is only about 1 to 2 kilometers per second left, while we need at least another 4.5 kilometers per second to land safely. Although still possible to achieve this, we need to use the remaining fuel very strategically. And from here, things get very uncertain because this is the theoretical way to make the landing as logistically feasible as possible. To save fuel for the final crucial deceleration, we need to use some external forces to help slow the spacecraft down. Putting the spacecraft into a low circular orbit around Mars would use up most of the remaining fuel, so we don't want to do that. Instead, a more sensible strategy might be to put the spacecraft into an elliptical orbit rather than a circular one. Once in an elliptical orbit, the spacecraft will follow a path that is closest to the planet, periapsis, and farthest away, apoapsis, from the planet. With this strategy, we can begin to use both atmospheric drag and Mars's gravity to help slow it down. Although it's very difficult, we'll use whatever assistance we have from the environment to slow it down. One way we can do this is to lower the bottom of the orbit so that the spacecraft cuts into the Martian atmosphere. In this way, the spacecraft will use some of the atmospheric drag to slow down before being pushed back into a higher orbit. If done correctly, Mars's gravity will pull us back down, and the process can be repeated, each deceleration bringing us closer to the velocity needed for a gentle landing on the planet's surface. However, we can't do this forever. Eventually, we will have to transition from gentle deceleration to a full dive into the Martian atmosphere. Creating a precise landing trajectory on Mars is complicated, as the planet is only half the size of Earth. This means that the angle of attack required to descend to the planet's surface is quite steep. As a result, the spacecraft will need a lot of power to reduce altitude and avoid bouncing back into space. However, we want to save the engines until the last moment, so the thrust to push the craft deeper into the atmosphere will need to come from another source. That's why SpaceX's original 2016 design for its interplanetary transport system included a hull capable of generating lift. Although Starship is much smaller than the original design, the principle remains the same. On final approach, Starship will perform a flip, entering the atmosphere with its belly and tail pointing up and its nose pointing down. This will create lift from the hull to push the ship at a steeper angle, giving us a better angle of approach to the Martian atmosphere. Once deep in the atmosphere, Starship will perform a full flip to begin the belly flip we've seen in tests on Earth. The goal of this maneuver is to create as much drag as possible, thereby slowing down as efficiently as possible. However, there is a limit to how much drag can be reduced by aerodynamic drag alone. When free-falling, there's a concept called terminal velocity. So, what do you think about this landing strategy? Can SpaceX overcome these major challenges? Share your thoughts in the comments. You can think of it like jumping down an endless pit. Your body will accelerate as you fall, until a point where the drag from the air and gravity balance out, and your rate of fall becomes steady. One way to cheat terminal velocity is to use a parachute, which increases drag and slows down this terminal velocity. However, Starship won't use a parachute, which means there will be a point where aerodynamic drag is no longer effective and will reach terminal velocity. On Mars, because the atmosphere is much thinner than on Earth, this terminal velocity is 5 times higher than on Earth. This means that compared to doing a belly flop on Earth, deceleration through the Martian atmosphere will be only 1/5 as efficient as it is on our planet. What we saw Starship do on Earth will not be directly applicable when it lands on Mars. So Starship will need to use much more powerful engines to be able to land successfully on the Red Planet. This is why fuel is such an important factor in making this flight happen. If everything has been done correctly up to this point, Starship's engines will fire one last time, turning the ship's tail toward the surface of Mars. And at that point, the fuel in the rocket's nose tanks will provide enough delta V to put the spacecraft on the right orbit with the planet's surface for a soft landing. However, this is a series of steps that must be perfect, and there is no room for error. You only get one chance, and a single mistake can mean total failure. With what we know, we can understand that landing on Mars will be an extremely difficult challenge for a giant spacecraft like Starship. For NASA, landing small and light vehicles on Mars is much easier because the ability to change the velocity of the fuel depends on the mass of the spacecraft and the engine performance. Specifically, each pound of fuel can only produce a certain amount of velocity change, and a lighter spacecraft will make better use of fuel than a heavier one. However, there is a limit to how much fuel we can carry to land on Mars. Starship would be easier to land if it were lighter, but SpaceX needs Starship to be large enough to accomplish Elon Musk's goal of building a self-sustaining city of 1 million people on Mars. SpaceX is currently working on increasing Starship's Delta V capabilities. They want to design a longer Starship V2 with larger fuel tanks, while still keeping the weight down. Additionally, 3 new vacuum-driven Raptor engines will be fitted to the next-generation Starship, which will increase fuel efficiency and increase Delta V capabilities. A third version of the Raptor engine is currently being designed and is expected to be more efficient, further increasing Delta V capabilities. However, there are other long-term solutions being considered. Recall that the outer moon of Mars, Deimos, requires only about 5.3 km/s Delta V to get from low Earth orbit to Deimos orbit. That's a lot more manageable. And imagine if we could build a Mars outpost or gateway in Deimos orbit. From there, we could refuel Starship to continue on to Mars with Delta V to spare, making the landing much safer. This would provide a buffer of time and reduce risk, making the landing on Mars much safer. So it's safe to say that landing a fully loaded Starship on Mars would be incredibly complicated. This is a situation where SpaceX can't be sure of the outcome until it's tested. We've already seen 2 failures with Starship launches alone, both of which exploded in mid-air. Learning how to land on Mars will likely be similar, and will likely face many failures before we succeed. SpaceX may even have to try many times before it succeeds. But we've accomplished the impossible many times over the course of human history. So why not again? What do you think about the possibility of landing Starship on Mars? This is a huge step forward for the space industry, and we'll continue to monitor its development. Don't forget to like this video if you find it interesting and share your opinion in the comment section. Subscribe to Space Now channel so you don't miss any updates about the space industry and interstellar exploration.